This is the solution to problem 458 of Halliday, Resnick, and Walker. Let's go look at the problem. We've got a fan that rotates with a certain rotational speed of 1,200 revolutions every minute. And we want to think about the tip of a blade at a certain point out there. And we're asked various questions about its speed and its acceleration. So as usual, let's sort of ignore all the details here, or the specific questions, and just go make sure we understand kind of what's happening. We've got a fan blade, and there's a particular tip of this fan blade here that we're interested in. And now what's going to happen is we turn this on and the fan blade rotates. Of course, my little circle doesn't. And it goes through and continues to rotate. I just have it drawn there as a single sort of rotation. So what do we want to do? We want to probably, we always want to think about sort of laying out I seem to be having trouble with my pen, a coordinate system here. And then we are going to sort of describe where that point is by drawing a position vector out there to that guy. And then we know it's going to have some speed, some velocity, and so we can draw the velocity vector as well. That's going to be perpendicular. And in fact, then when the object moves, it's going to go around in that circle that's traced by the line in red as it goes around. So we can sort of watch this process go. So notice the position vector and the velocity vector, their magnitudes don't change, but of course their directions do. As it goes around, each one of them rotates around a full 360 degrees as well. Now we know that even though the speed is staying constant, that there's other thing that goes on is that there's a change in the velocity vector direction, and a consequence that produces an acceleration. That's an acceleration, and we know that acceleration is directed in towards the center of the circle. So we'll draw that vector there in yellow, and once again, we'll sort of run the animation. All those vectors stay same constant length. Their magnitudes stay the same, but their directions continue to change. So, all right, that's our sort of description of the sort of situation. Let's go look now at the specifics of the problem. The first piece says, what distance does the tip move as it goes through one revolution? Well, so we're asked for the total length of this circumference here, and you probably know the equation for the circumference of a circle, but this is the way we're set up here. You don't have to know anything in physics because it's on the equation sheet. So there it is, the circumference of a circle, 2 pi times r. So let's just drag that equation up here. And we will explicitly then put in the numbers for that. We know that the distance r in this case is 0.15 meters. And so we'll put that in there and calculate the circumference, 0.942 meters, a little bit less than 1 meter. So that's the answer to part A. The second question then says, what's the tip speed? So how fast is this thing going? Well, we're not given that directly, right? We're told how many revolutions it takes in a certain amount of time, so that's clearly related to how fast that thing is going. Let's think a little bit about that. The equation for the speed is distance divided by time, and in fact, in this case, we know the circumference. That's what we just calculated up here. And so what we need is how long it takes to go through one full revolution. And it's clear that we can find that from this number up here, this 1,200 revolutions every minute. So that's not outrageously challenging, I think. But if we go back and look at the questions, we realize actually that's part D of the problem. So we actually are going to solve part D before we can come back and do part B. So what's the period of the motion? Well, if we know that every minute, which is 60 seconds, it goes through 1,200 revolutions, the time it takes for one is clearly that 60 seconds divided by 1,200. And if you calculate that, comes out to be 0.05 seconds is the period. And so now we're in a position to be able to go back up here and do our part B that we had started with to find the speed. Now, generally, as I say, I don't like to just take this stuff and put it from here back up into this equation, because it gets a little unclear as to how you're working if there's not a logical kind of progression. So what I did here is just rewrote the equation, circumference divided by the period, put in the numbers now that we know, and calculate that as 18.8 meters per second. So notice that's actually moving pretty good clip, right? 20 meters per second, that's pretty fast. So, but we've got this thing going around, the fan blade is going around pretty fast, so even though the radius is relatively small, that translates into a relatively high speed. So now I think we're ready to go on and do part C, which is what's the magnitude of the tip's acceleration. And once again, we sort of know that equation, v squared over r, but we don't have to know it. There it is on the equation sheet. This is the upper left-hand corner of the equation sheet, and this gets a little crowded, so it's worthwhile. We're going to be using some of these other equations a little bit later in the course, but this centripetal acceleration is labeled on the equation sheet a sub c, primarily because the one that's above here is called the tangential acceleration, and that's how, if something is speeding up or slowing down as it's going around, that equation comes into play. For us, we're just looking at constant speed as we go around a circle, so all we need is the v squared over r that comes with that equation. So there we have the v squared over r. It's really just a matter of putting in the numbers, the 18.8 meters per second, square that, and then divide by 0.15. And it may not be that surprising that that comes out to be a pretty big number, right? 2370 meters per second squared. Now, again, if you're working this problem, it might be the first time you've seen accelerations that large, and you might have thought, oh, I must have made a mistake somewhere. That can't be. That's 237 times the acceleration that objects experience under the force of gravity. But actually, that's not atypical for something like this. And we'll come to understand how that can be used in things like centrifuges, because it effectively, well, we'll study that later when we talk about forces. For now, I think we're done, because this acceleration is the magnitude of the acceleration for the for part C, and we've done parts A, B, and D already. So the problem is finished.